Good morning everyone. In today's class we'll be starting with the design of the DC machines. Okay. To start with, in this video we'll go through the output equation and the specific loading. Okay. So the first one, output equation. So what an output equation is, it is an equation, okay, that gives a relationship between the output of the machine, okay, and the dimensions, okay, which are decided by the specific loading or the specific loads. Okay, so here we have two types of specific loads, electric specific load and specific magnetic load. Okay, so these two, okay, are related with the output of the machine, right? So to start with, the power developed by the armature, right, so which we all know by the basic equation, that is E into Ia 10 raised to minus 3 kilowatt. And then the induced EMF of DC machine we have, okay, so which is E, which is P and Z, right, by 60 into A, right. So by that, right, so here this is ZA is nothing but, right, so it is, Z is number of conductors, total number of conductors. So this ZA becomes conductors per parallel path. Okay, so that is what the ZA is taken as it is, right? Right, so by taking these two equations, okay, that is equation 1 and equation 2, right, so the power developed by the armature PA, okay, so we are substituting the value of E from 2 in 1, right, so what is E is P and ZA 5 by 60, right, so that is what P5 ZA n by 60 into 10 raised to minus 3 kilowatt. Okay. So next we'll have the help of these two equations. Okay, so BAV, that is a flux density, average flux density, right, and then the Q, right. So this is the specific magnetic loading, okay, so which is given by this equation P5 by pi dl Tesla, and this Q is the specific electrical loading, okay, so which is given by these relations, okay, right. So the definition of these two and this equation how we have got, we will see in the next part. Okay, so next, right, so from this equation, that is BAV, which is equal to P5 divided by pi dl Tesla, okay, so from that P5 will be equal to B average into pi dl, that is what the value for P5 is taken, alright. And then next we are going to take the relationship for Q, right, so we have ISZA, okay, so ISZA will be pi d into Q, okay, so pi d into Q, so those values we are substituting in this equation. PA phi Z we had, okay, so which is B average pi dl, and then we have ZAIA, okay, which is nothing but Q into pi d. So those things are substituted here, right, so P5 substituted as B average pi dl and ZAIA substituted as phi d Q, okay, into 10 raised to minus 3, okay, so the rest remains as this n by 60 is as it is. So when we simplify this equation, we get pi square by 60 B average into D square ln into 10 raised to minus 3 kilowatt. Okay, so that is the equation we have for the output power, right. And then next, right, so we are bringing this n on this other side, that is PA by n, okay, PA by n is equal to C naught D square L, that is this whole thing which is in the bracket, that is pi square by 60 BA average into Q, okay, so this thing is now actually as given as C naught, okay, C naught into D square L, because n is taken to this side, okay. So now, right, so D square L will be P by n, PA by n into 1 by C naught, okay, so this is the equation that we have, equation number 3. Right. So this D square L is equal to PA by n into 1 by C naught. So actually this is the equation, that is the output equation we have, right? So we have this D and L. We'll see they are nothing but the dimensions of the machine, okay? That is the diameter and the length, axial length, okay? This is the about the machine dimensions. And then we have PA, which is the output power, right? And C naught, okay? So output coefficient, which involves nothing but pi square by 60 B av, that is the average flux density, which is nothing but the magnetic loading, specific magnetic loading, and Q, which is specific electrical loading, okay? So that is what, so we had said in the beginning, the output equation is the one which relates the output of the machine, okay, with the dimensions, taking into consideration the specific loading. So this C naught, right, represents the specific loading, okay, which is combination of specific magnetic loading and specific electrical loading, okay? So from this, so C naught, okay, C naught is known as output coefficient, okay, and C naught is equal to, okay, so from this basic equation it is pi square by 60 into BAV, that is the B average, into Q into 10 raised to minus 3. So this is the C naught, that is the output coefficient, okay? So now we can see that the equation 3, as I said earlier, right? So it is what? It relates the power developed by the armature and the size of the machine, okay? That is size of the machine, this equation, right? So this D square and L decide the size of the machine, and we have this output power. Okay, so now we'll see the terminology that we have used, right? So P is number of poles in DC machine. Flux is the air gap flux per pole, okay? Usually we have it as flux per pole, right? That is the in Weber. And D is the diameter of the armature in meter. L is the gross length of the armature in meter, okay? Then B average, that is the average gap flux density in Tesla, okay? And Q is the specific electrical loading. Then IA is the current in the armature in ampere. A is number of parallel paths, and IA by A is the current in each parallel path, okay? And then we have the ZA, that is the number of conductors in each parallel path, whereas Z is the total number of conductors, whereas ZA is the number of conductors per parallel path, okay? And then the last one we have is the capital N, which is the speed of the armature in RPM, that is revolutions per minute. So these are the notations that we have used, okay, to derive the output equation. So next we'll see the relationship between, right, the power developed, right, and the output in DC generator and DC motor, because we have just taken it as DC machine, right? So therefore, so first one, relation between output and the power developed in DC generator. So PA is equal to, as we know, E into IA into 10 raised to minus 3 kilowatt, okay? So E is, right, by basic V plus IARA, okay, and IL plus IF, which is the IA, right? So from that we get PA is equal to VIL, okay, then VIF plus IA square RA, right? So because this IL plus IF is the IA, so IA square RA. So this is the equation that we have, right? So what and all it allows here is the power developed, okay? So it should be able to fulfill the voltage, okay, then the losses, okay? So the losses are of here of two terms. V into IF is the loss, okay? P, as we know, P is equal to VI, right? So this loss is the loss that is taking place in the field winding, okay, the copper losses in the field winding, and IA square RA, right, I square R, the basic equation, the losses that are taking place here is IA square RA in the armature. So the total power that will be developed, right, so it includes the output plus the losses, that is what it is, right? So here we have the power PA, okay, should be greater than VL into IL, right? That is why, right? So because it has to accommodate the losses, then also the output. So the power developed is equal to the output plus the losses. Here it is the copper losses in field winding and copper losses in the armature winding. Okay, and these losses are 5 to 7% which are assumed. Okay, so what will happen is the PA, it has to be 1.05 to 1.07 times the output, that is PA, right? We have said it is PA greater than V into IL. So how much times it is greater is 1.05 to 1.07 times it is greater. The next we have relationship between the output and the power developed in DC motor. Okay, so the power developed EA IA into 10 raised to minus 3. So EA here, since it's a motor, we have V minus IA RA into IL minus IF. Okay, so the basic equations. So into 10 raised to minus 3. Okay, so PA is equal to V into IL minus V into IF minus IA square RA. Here also the power developed. Okay, right? So it is the total power, right? That is the output minus the losses. Okay, so that is what here it is. Okay, right. So the equation 4 that we have, okay, it is related to the C0, that is the output coefficient. It is clear that the volume and size of the machine decreases by designing the machine at higher speed, okay, or by increasing the output coefficient. Okay, it's an equation 3, not equation 4. Okay, so you can see this is the equation, right? So I want to have this small. Okay, if the dimensions have to be small. Okay, right, so this is diameter and the length. Okay, if this has to be small, right, so the denominator values have to be high, right? Therefore we should have either the machine with higher speed or with the higher output coefficient. The next part that we have in this is selection of specific loading. Okay, since we know that the output equation, right, involves the specific loading, that is the both specific magnetic loading and specific electrical loading. So we should know about those, right? So specific magnetic loading, right? So what it is defined as the ratio of total flux around the air gap to the air gap area. Okay, so flux by the flux area. Okay, that is what. Okay, so it is the taken. So it is equal to the average flux density in the air gap of the machine, right? So we know that air gap is a must, right? Because we have one part that is stationary, the other one which is rotating. So it is always advisable that we have some gap between these two, right? So and the gap, if it is too much, since this air gap is also the part of the magnetic circuit, right? So the higher the air gap, what happens is the leakage will be more, that is the flux linking will reduce. Okay, so that is what the care has to be taken, and also we cannot make it 0, right? So which will make the basic principles itself a false one. Okay, that is what. So that is what is taken. So average gap flux density, B average, is equal to, it is flux by area. So it is P phi by pi d L. Okay, so where we have seen P is the number of poles and flux phi is the flux per pole. Okay, and then we have pi d L. Okay, where d is the diameter and L is the gross length of the armature. So this is what we have the definition for specific magnetic loading. Okay, so it is nothing but the flux density, or you can have it as average flux density at air gap. So next we will see specific electric loading. So it is defined as the total number of ampere conductors on the armature per unit circumference of armature. right? So what does it mean? Total number of ampere conductors on the armature, okay, armature per unit circumference of the armature. So that is the high value of the current that is being produced, right? That is, if you can produce more voltage, okay, so then the in a small area, then the loading is more. That is what the meaning is, okay. Therefore specific electric loading is equal to Q, okay. It is denoted by Q, which is Ia by A into Z pi d. Okay, so what it is? Ampere conductor, okay, right? So ampere conductor, right, divided by the per unit circumference. So we know that Ia by A will be current, right, into conductor, ampere conductor per unit circumference of the armature, since pi d, okay. So that is what we have, okay. So it is Ia by Za. So where again in the basic equation, where Z is the total number of conductors, whereas Za is Z by Ia, sorry, Z by A, that is conductors per parallel path, okay. So this is the basic that we have. Next, seeing some right, so points how this affect, that is the selection of specific loading, okay, whether it is specific magnetic loading or specific electrical loading, what effect it has on the design, we will see, okay. So first step itself, that is the design process, is initiated by assuming suitable values, okay. This suitable values of what? Suitable values of the specific magnetic and specific electric loading, okay. So that is the assumption. Only we start with assuming some values for these, right. So if you can have a proper correct, right, a technically correct assumptions made, then the design would be the good, or you can say the best one. So that is very much important. The next point is main dimensions of armature and other parts design is dependent on the proper selection of these loading, okay. That is what we said, right? The output equation, it has what? It has the output, that is the PA, then the main dimensions of the armature, right? So main dimensions we went where by D and DL, right? So D square L was there, right? So to depend on the proper selection of these loading, which had C naught, where C naught was involving B average and Q, which are the specific magnetic and electrical loading respectively, right? Then the average value of air gap flux density is limited, okay, to prevent maximum flux density at the tooth, okay. So this is one thing, right? So now we get some limitations, right? So what it says, the average value of air gap flux density, right? So this air gap flux density we are speaking of is nothing but BAV, that is the B average, that is the magnetic, specific magnetic loading, okay. So it has got its limitation, right? So what it is limited? It is limited by right, the flux density at the tooth, okay. So that is what we have. So at the tooth, right, so that decides, right, right, we'll also tell next, we'll see why there is that limitations of flux density at the tooth, right. So maximum flux density at the minimum section of tooth should not exceed 2.2 Tesla. This is what, right? So the maximum flux density at the minimum section of the tooth, okay. So we have seen the slot and tooth arrangements, right? So when we went for the procedure for finding the MMF, that is the ampere turns, right, so of the tooth, right, so that the shape is not uniform, right, so it is having a tapering, right. So there what we have to take care is the flux density, that is the maximum flux density at the minimum section of the tooth, okay. So that where we have the small size of the tooth there, okay, should not exceed 2.2 Tesla, okay. So what happens if we are exceeding the value, right? So if you are using, right, so what will be is, so if I want to have more flux density, right? So it means that flux density is flux per area, so I'll have to have more flux. So MMF is flux into reluctance, right? So if I want more flux, right, then MMF required would be large. Okay, it will be very large. Okay, so what and all it will lead is, it will lead to increased copper losses in the field winding, right? Why field winding? Right, so field winding, right, the one which is responsible for production of the flux, required flux. As we know that flux is proportional to the current that is flowing through those winding, right? So, and also we know that losses, copper losses is I square R, right? So if you want to have more flux, more I, okay, right? So the more I, the losses is also more, because losses is I square R. Okay, that is we have the limitation, right? And then we have the higher cost of copper. Okay, so copper, the cost would be more, and the large magnetizing current would be required, would be large. Okay, next is even the iron losses in the tooth will be high because of increased flux density in the tooth section. Right, so iron losses are related to the magnetic, right? So as we have higher flux density, right, the iron losses in the tooth will also be more. Okay, so this is the reason, right? So we have these limitations, so for which we are limiting the magnetics, the specific magnetic load, that is B average or BAV, that is we have used. Okay, next we'll see the values on which the specific electric loading depends. So what and all it depends? It depends on, electric loading depends on ventilation system, armature reaction and commutation, right? So what is the electric we have is more current, right? So by basic definition, right, so we have seen it, right? So here what is this is Q. Okay, so if you want to have Q value more, means the current value will be more. Okay, so that is what, right? So if I want to have that, right, it depends ventilation process, because IA is more, or I is more, means I square R losses will be more, right? So we'll have to make, right, so I square R losses lead to rise in temperature, so, right? So if you are having a better ventilation system, okay, so then it would be easy. Then armature reaction. Okay, so we know that the higher the value of the IA, the flux due to IA also is opposite to the main flux, right? So since that armature flux depends on IA, higher the IA, higher the flux, which will lead to higher opposition to the main flux. And then commutation, right? So commutation is converting that AC to DC, right? So that also will become a problem, right? So that were the things, right? The next one is the value of specific electric loading, okay, for interpolar machines is comparatively high compared to without interpoles. Okay, so that is what we have, right? So we know interpoles were there because of armature reaction, right? So whatever the flux that was reduced, okay, due to the current in the armature conductors, right? So that is to be provided by the interpoles. Okay, that is the small poles between two main poles. Okay, all right. So now, right, so this is what we have seen. Okay, so from the equation, right, so that is, right, the basic equation, that is the power output, right? The output equation, we have C naught, okay, D square, that is the D square ln. Okay, so now, right, so it means here, right, so D square L and N, right? So having higher the value of B average, that is the specific magnetic loading, and higher value of Q, that is the electric specific electric loading. Okay, if this is high, then this will be high. That is the advantage that we have. So that is what, right, the choice of higher specific loadings. Okay, that is higher value of BAV and higher value of Q, right? They have following advantages. What are the advantage? Reduced in the volume of the machine, right? So D square ln, right? If this is constant and if this is high, then I will have lesser value for this. Okay, that is what is there. And reduction in the size of the armature, right? Again, because of this values, right? And then lower cost of materials required, right? So when I say size is small, right? So and the volume is less, then the materials required would be less, right? So and the cost associated with them also will reduce, right? And then total reduction in the weight of the machine, since there is a reduction in volume and size, right? And then overall cost of the machine also will be reduced, right? So these are the advantages that we have, okay, for having higher values of the specific loadings, that is the specific magnetic loading BAV and specific electrical loading Q. Okay, right. So next what we have is, see that what for cheap and small size machine, the values of specific loading must be highest, that is whatever is a possible highest value we can take, okay, we can make use of those values. Okay, so if you want to have a cheap and a small size machine, okay, but right, so we have already seen few disadvantages, right? So it's not always possible to have the loading at highest possible values, right? So there are disadvantages due to both specific magnetic loading and also due to specific electric loading. So first we will go through the disadvantages of having higher specific magnetic loading, okay, more right, so flux, that means BAV, more BAV means more specific magnetic loading. So BAV is flux per area, so more flux, the losses, right? And then we require large requirement of MMF, right? So MMF, because MMF is equal to flux into reluctance, more flux means more MMF. Then higher field copper losses, because the current should be more, okay, so to increase the flux, so more the current means more the I square R losses, okay. And then higher tooth flux density, okay, that is what it, a smaller size, right? So we'll have large values, that is what. Then tendency of saturation of magnetic parts, okay, so if you're having a higher value, right, the saturation, that, or if they're working very near to the saturation levels, right, if they become saturated, right, then that will lead to different types of problems. And then increased no load current also, okay. So I naught was the vectorial addition of the I naught, Im and IL, okay, the magnetizing current and the loss component, okay. The next disadvantage is, right, with the higher temperature rise due to higher losses, right? So as you said that losses are more, right, and these losses are in terms of heat, right? So the temperature rise also will be high, okay. And then increased noise, okay. So these are the disadvantage that we have, right, when we are going for higher specific magnetic loading, okay. Then we'll see what are the disadvantages of higher specific electric loading, okay. So what we have is increased armature copper losses, okay, because the Q is nothing but, right, so it was Q, which is this electric specific loading, right, it is nothing but Ia ZA by pi d. So if Q has to be more means Ia has to be more, so therefore that armature copper losses will be more since Ia is more. Then increased reactance voltage, okay, fine. So because if Ia is more, then the flux, all those things, right. And then inferior commutation, okay, so the conversions of that AC to DC will not be of better quality or at high values. And then we have increased field excitation, okay, so causing more field copper losses, okay, so that is also the disadvantage, okay. Then reduction in overload capacity, okay, this is very much important disadvantage, right. So usually we know that, right, so machines are so designed that they can operate over their load, okay, for some small period, okay, so according to the design will be done, right. So that is then taking into consideration the losses, okay, the temperature rise, fine. But since right, so even at the normal working, right, since the losses are more and the heat losses are there, right? So the temperature rise will be more even though they are working at the loaded or lesser than the loaded capacity, right? So therefore it will be very difficult to work such machines at overload capacity, okay? And then higher temperature rise due to increased copper losses, that is I square R losses, which are in form of heat, which will lead to the temperature rise. Okay, so when going through this, right, so first we saw the advantages, right? So with those advantages we thought that we can have very high values for these specific loading, that is specific electric loading and specific magnetic loading, right? So since now as we have gone through their disadvantages, right, so what will the takeaway is that, right, higher values of specific loading, right, will affect the performance, okay? Impair the performance means will affect the performance of that machine, right? So what has to be done is, right, an optimal value has to be selected, right? So where the performance is also met, okay, and also the advantages due to the high specific, right, especially the size and the cost, both can be achieved, okay? So for that, right, so we have few values, okay, right? So for the specific magnetic loading and specific electrical loadings for these ratings, right? So when output in this you can see output, fine. So if it is a 5 kilowatt machine, okay, so then B average, that is the specific magnetic loading, will be 0.43 and the Q, that is the ampere conductor per meter, will be so much, that is 50,000, right? So if it is, right, so already we have started, even we said that the designing started with these values, right? So we'll be selecting these values, right, so which are to be optimal, okay, right, so which will give us the better performance with cheap and the possible small size machine, right? So similarly this table has the different values. If it is a 10 kilowatt machine, what should be the specific magnetic loading, electrical loading, then for 50, 100, 200, 300, right? So 500, 1000, 1500, 2000, 5000 and 10,000 kilowatt output machine if you have, right? So the range, that is from 5 kilowatt to 10,000 kilowatt, okay? So what are the values of the specific magnetic loading and specific electrical loading that we can have, right? So it is, these are the values, okay? So by choosing these values, okay, then we can design the machine. Thank you.